Hello, my name is Wang Yunze. Today I will introduce our capstone project. It's about the dual stream wind tunnel. The turbulent mixing layer has been widely studied over the years, both in experiment and the computation. It plays an important role in many engineering applications. They govern the rate of mixing in combustion chamber and flow reactor. They are also responsible for most of the noise generated by propulsion system. This project is resemble and adapts the dual stream wind tunnel, conduct a series of experiments, set up virtual simulation model to justify the results. Our main goal of this project are conducting the experiment both in real and CFD model, and under certain airflow condition make adjustments in model for further advanced experiment. They then extreme a few interesting points raised by other researchers. And then the next part is assembling the wind tunnel. 5 steps. The first is assemble the step motor system. The second, we will clean each part. Then we will install the wind tunnel panel. The first one, we will install the step motor and sensor and VFD. The last one, when we finish the assembling, we will test the wind tunnel. Our wind tunnel is a classic dual stream wind tunnel. The structure of our wind tunnel is similar to the one shown in this picture. Two identical centrifugal blower are south of the airflow, and the two airflow going through the two tunnel will meet at the end of splitter plane. Airflow will exit the wind tunnel after the testing section. Since original step motor come with the wind tunnel are old, we bought new step motor and matching controller to replace them for easy to integrate the step motor with existing equipment. We wrote a MATLAB script to control the movement of step motor through several points instead of using the software come with the step motor controller. Due to the COVID-19 restriction, we focus on the simulation part. The ANSYS Fluent used by here to simulate the flow in the wind tunnel. As shown in this picture, our model is two fluids with different velocity merging behind the splitter plant. We are simulating this part, and our model looks like this. We get the similar normalized mean velocity from simulation and experiment results. This accuracy of our model are using this model to simulate more cases, such as finding the side wall divergence angle and self-similarity distance for different velocity ratio. The next part is difficulty to COVID-19. COVID-19 brings us quite a few difficulties. The most significant one is that we can't go the lab anymore, and when the assembling process is halfway through. And this several implications on our project. Some of we had can't be achieved anymore. And for example, we since can't finish the resampling in time, and we can't run experiments on the wind tunnel before the end of the project. COVID-19 also means that all teaching activities are now online, which include meeting with our supervisors, although we get used to have a meeting on Zoom very quickly. The last part is conclusion and recommendation. In the higher and lower velocity cases, all these cases can achieve self-similarity of mixing layer. The stream distance in which self-similarity is achieved decreases with increased velocity ratio from 0.5 to 0.7, and the downstream distance increase with increased velocity ratio from 0.8 to 0.9. For different velocity ratio, a zero pressure gradient needs to be maintained in the wind tunnel to get some reliable results. The divergence angle for different velocity ratio are acquired from simulation parts, which can be used for future experiments.